I'm going to go over sections 5.4 and 6.1. So 5.4 finishes up chapter 5, of course, and then 6.1, we're going to go over discrete probability. 5.4 is on actually like counting principles, which is sounds like it should be easy, but I'm going to make it a lot harder than just counting. Okay, so counting principles. The first counting principle your book goes over is just the fundamental counting principle, and it's very basic. Like, and it just goes over an example of about license plates, and this is on page 239. But it says, look, license plates in a certain state contain 3 letters, and then 3 digits, right? How many different license plates can be made? Well, you've got to think of like how many letters there can be and how many digits, and then you just multiply across. And it's very, very basic. So like there's 26 letters in the alphabet, right? So 26 times 26 times 26. Digits, you can go 0 through 9, with the license plate. So that's really 10 digits. And you can multiply those 10 times 10 times 10. So you wind up in your book says this, it's 17,576,000, right? Different license plate options if you have 3 letters and 3 digits. Another one is like social security number, same thing. Like how many is it? Is it 9? Yeah, you have 9 digits for social security number, right? And let's say they could be any 10 0 through 9 on any of them. So how many social security numbers, right? Well, it's just going to be 10 times 10 times 10, right? So it winds up being 10 to the 9th power, right? Because it's going to be 10 multiplied 9 times. And that's a big number, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 billion, right? Yeah, you got a billion options for social security numbers. Now you've got to be able to use the number, every number has just kind of the same opportunity of being used, and that's how many. I know it's a little different with social security numbers, like the numbers mean something like where you're from or where you were born or something like that. I don't know, but I don't think it's just kind of random. But if it was random, you'd have a billion different social security numbers, which is kind of interesting. And this happens like Sonic a few years back. This is kind of an example that kind of pops up on here, and it talked about Sonic. The commercial said, so many different drink options. So if we looked at one a little differently, let's say we had, like 7 different sodas. Okay, we had to choose one, and we had 8 different, let's say, extra flavor shots. We'll call them flavor shots. And then we got 2 ways we can do ice, right? We could do either ice or no ice. And I wanted to look at I've got to choose one of each of these, right? So we're not going to be mixing sodas. We're not going to be mixing flavor shots, which they calculated into their number, which makes sense. But if I've got to choose one of each of these, and I wanted to know how many different options I have, well, it's just 7 times 8 times 2, okay? 56 times 2, I believe that's 112. So you got 112 options if you've got 7 different soda drinks to choose from, 8 different flavor shots, and 2 different ice options, right? Now, of course, this is only choosing one of each, okay? This is choosing one of each. If we're going to choose 2 out of 7 or 8, that means we're going to have to use a different kind of counting system, okay? Different kind of counting system. And that kind of leads us into the first one, which is called permutations. So permutations, and I'm going to go how the book defines it. It says the word permutation is another word for ordering. When we count the number of permutations, we are counting the number of different ways that a group of items can be ordered. So order, I want you to think order matters. Okay. Order matters. Like if I gave you, let's do a very, very basic example. If I gave you 4 different letters, let's do 3 so I don't have to write out as much. Let's say I gave you the letters A, R, and T. And I ask you, how many different ways can A, R, and T be ordered? This would be considered their permutations, okay? So if we think about it, it could be, I mean, art is one way, right? I'm not going to write the boxes out. Let's say ATR, right? That's another way. Then let's put the T first. So TAR, and then TRA, and then R can come first, right? RAT, RTA. 1, 2, 3, 4, 5, 6. Is that all the different ways? Yep, that's all the different ways that these 3 letters can be permutated. Okay, these are all the ways. So 1, 2, 3, 4, 5, 6. There's 6 different ways that 3 letters or 3 numbers could be ordered. Okay, so these are all the permutations of the 3 letters ART. Or if we had 3 numbers, 1, 2, 3. I mean, it doesn't matter. But these are all the different ways they can be ordered. Okay. Now, if you want to count the number of permutations, it's kind of nice. So your book goes over this as like the definition on page 240. It says for any positive integer n, the number n factorial, and we'll go over what that means. And it's pronounced n factorial and is equal to the product of all integers n down to 1. Now look, if we're going to use every letter I give you, then to find the number of permutations, we can just do n factorial. The way you find n factorial is you multiply descendingly. So look, there were 3 letter options here, right? 3 letter options. So if I wanted to find the number of permutations, I just have to find 3 factorial. And the way you find 3 factorial is you take the number and then you multiply it down descendingly. 3 times 2 times 1. So 6. Okay. So let's look at another example. This is kind of a goofy one, but let's say like there's 7 books in Harry Potter, right? Okay. So we got 7 Harry Potter books. Okay. So let's say you're a librarian and you know someone checked out all the Harry Potter books and you go back to put them in the library, you know, in their one little section, and you have 1 of each. Okay, that's what's important. You have 1 of each. And you start thinking, you know, I wonder how many different ways these 7 books could be ordered, right? I mean, we could order them, of course, descendingly or increasingly, right? That would be kind of the correct way of ordering them. But let's say you are an outside of the box thinking librarian, and you just wondered, like, how many different ways? You know, 1, 4, 2, 3, 7, 8, you know, whatever. How many different ways could you order these books? Well, if you wanted to know the number of ways you could order 7 books, it's just 7 factorial. Now look, let's bring this up in the calculator. I've got my calculator. I charged it up. It should be charged, I should say. I don't have to use the, yes. Hey, look at that. Okay. Factorial is in your calculator. So I'm going to hit 7 first, and it's going to take me a minute to find factorial because I haven't found it in a little bit. Get some of that glare off. I believe it is stat calc. Yeah. Stat calc. Maybe not. Oh, no, I know what it is. Is it math? Prob, yeah. So it's math. If you want the factorial, you hit the math button, which is right there. You guys see that right above the x to the -1, right below the alpha key, math, and then go over to probability. Probability, which is up here. And you can see the fourth option. I know it's hard to see with this, but the fourth option is that factorial button. So we're going to choose that, and boom, we've got 7 factorial in our calculator. I wish this showed up better. I know this is just the camera being kind of goofy. But when I hit enter, it's 5,040. Okay. So there, which is crazy. There's 5,040 different ways to order anything with 7. Okay. So if you take 7 and you order all 7, now here's the thing with this factorial, you have to use all 7. Okay. You couldn't have 6 and only use 6 of them out of the 7. That's a different formula we're about to get to. Okay. You have to use every single one of them. Okay. You have to use every single one of them. I'll give you another example. Let's say you start a garage band with your buddies, okay? And you know 4 songs. You've worked your tails off to get these 4 songs, sounding decent, okay? And then the local coffee house calls you up and they say, hey, do you want to start a world tour? You say, yes, I do. They're going to say, okay, well, you can start it right here at our local coffee house. And then they go, how many songs do you have? You go, oh, we know 4 songs. And that's perfect. Okay. Just come in, play your 4 songs. We'll give you some free coffee, and that's how we're going to pay you. Okay. And then you and your bandmates get together and you think, hey, we know these 4 songs. We're going to have to play all 4, right? Because that's all we know. And they want us to play 4 songs. And you think, well, how many different ways can we arrange this set list? How many different set lists? Right? I mean, you could arrange them like, 1 through 4, 1, 4, 3, 2, 4, 3, 2, right? I mean, well, if you want to know how many different, if you have to play all 4 songs and you want to know how many different ways you can arrange these, it's just 4 factorial. Okay, so 4 math prob, oh shoot, hit the wrong button. 4 math prob, and then go down to 4. 4 factorial is 24. 24 different set lists. Now look, I want you to know this is just 4 times 3 times 2 times 1. Okay. 4 times 3 is 12, times 2 is 24, times 1, 24. Okay. It's the same thing. There's just a button in your calculator whenever you get kind of bigger numbers. Okay. 4 factorial. Kind of cool. Okay. Okay. So that's if we arranged everything into different orders. Well, if we're going to arrange if order still matters and we want to arrange things, but we're not going to use the entire group, it's a different formula. And your book goes over this. Now, you don't have to memorize this formula because it's in your calculator, which is quite nice. Okay. But this is on the top of page 241. It says a permutation of R items chosen from N. Permutation. So it's still considered a permutation, but now we're going to choose a certain amount of items from the group. So they say of R items from N. So R is the small group, N is the big group. Okay. And then where order matters. I'm paraphrasing this. Because we're going to get to the second type of this counting kind of permutation, and order is not going to matter. So that's why I'm emphasizing ordering mattering here. So permutation of R items from N. So now instead, let's say 4 songs, but the coffee house says, hey, we only want you to play 3 songs, right? So let's think about this. Let's say we have songs A, B, C, and D, okay? But they only want us to choose 4 songs. So it's not going to be 24 now. I mean, we're going to have like, we could do ABC, right? We could do ABD, right? Because they only want us to choose 3 songs now. We could do ACB, because order matters. That's not going to be the same as this one. Okay, guys? Because order matters. So these two are going to be considered different. Okay, I should have flipped this around. So we do ADB. Okay. Then we could do, oh my gosh. I mean, I could keep going and going and going. Okay. My brain's starting to hurt a little bit. But if I want to know this, it's a different kind of formula. And so the formula is written there. So now it actually looks like this. Use this notation, NPR. Remember, N is the big group, P stands for permutation, and R is the number of the small group, And it equals N factorial over N minus R factorial. So I'm going to go back to this example, and I'm going to do one by hand, and then we're going to do it in the calculator to show you how you get it in the calculator for, really easy. So let's say I know 4 songs, but I can only play 3 now, right? And look, it's a set list, so order matters, right? If I play ABC, it's going to be different than ACB. That's a totally different set list, right? So how many set lists? I'm going to say hint here, order matters. Okay, I'm going to pop it in this formula. Now I've got to realize the big group is 4. I know 4 total songs, right? So N is 4. I'm choosing 3 of those songs. So that's a small group, of R items from N, 3 from N. So this notationally, it looks like this: 4 permutate 3, and it's going to be 4 factorial over 4 minus 3 factorial. Oh, you know what? Okay, this was just a very big coincidence that this is going to be the same answer. Give me a break here. I'll give you an example where it's not. Okay, but notice this will be 4 factorial over 3. 4 minus 3 is 1. 1 factorial. Well, that's just okay. Oh, horrible example, Robert. That's what happens when I make something up on the fly. Okay. It still winds up being 4 factorial. Let's do one that isn't like that, so I can show you a better example of it. Okay. Let's say, okay, this is a good one. This is kind of a classic example. You've seen a lot of stat books. Let's say I have 12 students in a class. And out of that 12, I have to choose, because for some reason we don't vote in the society, okay? In this made up society example I'm giving you, I have to choose a president, vice president, and secretary. So president, vice president, and secretary. And I want to know how many different permutations can I have, right? Now realize order matters here, because I could choose Jimmy, Joe, and Tom to be president, vice president, secretary, and flip that around and say Tom, Jimmy, Joe, and it's a totally different permutation. Okay, so look, order matters. I'll do one here in a minute where order doesn't matter in the same kind of situation. Order matters, so that means we have a permutation. So look, I've got to kind of think of what's the big number, what's the small number. Well, I've got 12 students in the class, right? So my big number is 12. I'm choosing 3 students out of that 12. So my little number is 12. Okay, so notationally, it looks like this. 12 permutate 3, and it's going to be 12 factorial over 12 minus 3 factorial. So we get 12 factorial over 9 factorial, right? Now I'm going to just find that in my calculator. I'm going to put it over here. Say on 12 factorial math 4 is a huge number. You know what? Let's just divide that automatically by 9 factorial. And you wind up with 1320. So there's 1,320 different ways we could have permutate 3 objects from 12 objects, okay? Where we're only choosing 3 out of the 12. Remember, like the Harry Potter book example, we had to choose all 12 out of the 12, okay? In this one, it was all 7 out of 7 books. In this one, we're choosing 3 out of the 12, okay? If we were doing all 12, we would just do 12 factorial, which is a huge number, okay? Now, you can put this directly in your calculator, and I'm going to go over the buttons real fast. First, you're going to put the 12 in. So you put 12. And then if you go to Math, Prob, and the second option there is NPR. Click that, and then automatically it'll make it. So you guys see that? No, it's kind of hard to see, but it's 12. Hey, 12P3, okay? Let's go back to the, okay. And then, ooh, hold on. It just doesn't like, the glare is messing it all up. So it makes 12P3. When you hit enter, you'll get the same thing, 1320, okay? You wind up with 1320, okay? So same thing. You can do it by, I say by hand. I mean, we're still using the calculators to find it, but you can do it within a few steps, or you can do it with one step with the function in the calculator, the stat function in the calculator, okay? Kind of neat. Now I'm going to find some in the book that they did. Try some, okay. Hold on. Okay, this is example 5.33. It says we've got 5 lifeguards. I'm going to just say LG. 5 lifeguards, okay, are available for duty one Saturday afternoon. So we got 5 lifeguards Saturday afternoon. There are 3 lifeguard stations. So I'm assuming only one can be at a station at a time. It says, how many ways can 3 lifeguards be chosen and ordered among the stations? So order matters here, right? Order matters because you might have the same 3 lifeguards, but then just move them around and you'd have 3 different stations, right? Same 3 stations, same 3 lifeguards, but different order, and we'd have a different permutation. So this would be 5 permutate 3, okay? 5 permutate 3. So again, I'm going to go to my calculator. I'm going to say 5 math probability NPR, click, and then put in 3, boom, 60. So we've got 60 different ways to order these 3 lifeguards around, actually 5 lifeguards around at 3 different stations. Okay. Let's see if I can dig one out of the homework. Okay, yeah, oh, this is a good one. So this is number 32 in your book, and it's about ice cream. Okay, so it says, this is 32 on page 245. It says a certain ice cream parlor has 15 flavors of ice cream. You want an ice cream cone with 3 scoops of ice cream, all different flavors. Okay, 3 scoops, all different flavors. Now, part A, I'm going to get to part B here in a little bit, but part A says, how many ways can you choose a cone if it matters which flavor is on the top, middle, and bottom? So I'm going to say order matters, right? If order matters, you know, like vanilla, chocolate, and the pistachio, right? But then pistachio, vanilla, chocolate would be considered a different permutation, right? If order matters, how many different cones can you have? Well, for this example, it would be 15 permutate 3, right? So 15 math permutate 3. You wind up with 2,730. Wow. So you could have 2,730 different permutations if the order matters, okay? If the order matters. Okay. Now, it's a good time now to start talking about, well, what if order doesn't matter, right? If order doesn't matter, that's called a combination. It's on the next page, like if you're following along from page 242, it's a combination. So combination, the thing is with a combination, the order doesn't matter unlike a permutation, okay? And it's calculated a little differently. So so same thing, we've got a big group, a small group, right? We've got the overall total number, and then we've got a small group we're choosing from. And it's going to be n factorial over r factorial times n minus r factorial. So the only difference here is you're dividing away the small group factorial. So what you're actually dividing away is the repetitions from each group. So like you're dividing away, like at the ice cream example, you're dividing away, if you chose like vanilla, chocolate, pistachio, you're dividing out all the different ways that vanilla, pistachio, and chocolate can be ordered together for a combination, okay? So for the same example with ice cream, so if we go back to that question in the book on page 32, part B says, well, in how many ways can you choose a cone if the order of the flavors doesn't matter? So order does not matter. Okay, order does not matter. Now remember, we had 15 flavors. We're choosing 3 for the cone. So this is going to be 15 factorial over 3 factorial times 15 minus 3 factorial. Okay, so we wind up with 15 factorial over 3 factorial times 12 factorial. Okay, and you're more than welcome to put that in the calculator. I'm going to show you, like, it's in like almost the same spot as the permutation. So if I do this for combinations, I'm going to say 15. Here we go. 15. Boop. It's 15 math probability. And look, right underneath the in PR is in CR. 3. Boom. 455. Okay. 455. 455. A lot less, right? I mean, remember, if the order mattered, it was like 2,730 flavors or different combinations, or say permutations, different permutations. If order matter, or if order doesn't matter, it's 455, and 455. And the reason is because you're dividing away all of the repetitive groupings. Okay, so your combination is always going to be smaller because of that, or it could be the same if some goofy things happen, but it's going to be smaller typically because you're dividing away all of the repetitive groups. So let's go back to, remember we had that class, was it a class of 12? Yeah. 12 students in a class. And let's say we've got to choose 3 to go to a conference. Why not? Notice order doesn't matter here. If I choose Jimmy, John, and Joe, it's the same as choosing Joe, Jimmy, and John, because there's no order that goes with just scooping up and choosing 3 students to go to a class. Okay. So if I'm gonna do the same thing, but this is a combination now. So 12 combination 3. So 12 math. 12 math probability. So 220. So if I have 12 students and I've got to choose 3 for a class, that would be 220 if order doesn't matter. Okay. So let's, the last part of this is actually the probability aspect of counting. And then let's look at, I'm going to just choose one straight from the book. So if we have, this is example 5.37 on page 243. It says, refer to the example of 5.36, okay? Of 30 people in the attendance, 12 are men, 12 are women. Oh, okay. 30 people attend a certain event, and 5 will be chosen at random to receive prizes. The prizes are the same. To the order in which the people are chosen does not matter. How many groups of 5 can be chosen? Okay. Oh, okay. So we've got 30 people at the event, and we've got 5. And then I'm going to do the one right before it first. It just asks for 30 to choose 5, 30 combination 5, which winds up being 142,506. That's if we had, 30 people at an event, 5 are going to be chosen at random to, I guess, win a prize. There's 142,506 different ways of groups of 5 if we've got 30 people. Now, A said, now on to 5.37. Okay. It says, refer to example 5.36 of the 30 people in the event. Let's say 12 are men, 18 are women. What is the probability that all the prize winners are men? So now we got to think about this. If all the prize winners are men, we've got to think of all the different ways 5 men could be chosen out of this really 12. Okay, I know it's out of 30, but in a way it's out of 12. So you'd have to do 12 combination 5, right? 12 of the group attending is male, and we want to know how many different ways can groups of 5 come up. Oh, Lord, how am I going to word this one? I want to know how many groups of 5 can be all male. Well, there's 12 men, so this is going to actually tell us the entirety of the male groups. Oh, that's horrible English. But let's do that. So 12 math 5. So it turns out 792 that doesn't seem okay. Yeah, no, okay. 792. So there's 792 groups that are just all male. Okay. And then if we wanted the probability that how many are all male, well, you just have to take 792 and then divide it by the total number of 5-person groups, right? These are all the groups mixed together, and there's 792 that can be only male. 42506. So we get slim chance, 0.0055, we'll say 6. So very slim chance you could just have all male or all female, right? If you wanted all female, you would just do 18 choose 5, right? And do the same thing if you just wanted all female. Question B, though, asks, what about at least one woman? And this is the question I wanted to get to because it brings in something from the previous section. What about at least one woman? Well, remember the at least one questions? At least one would be 1 minus the probability of all men. It was that not conjugate, the complement, right? So it would be 1 minus 0.00556. So we wind up with calculator. .9944. Okay, 0.9944. So kind of goofy. I want you to look at those though. They pop up. So for homework, it actually starts, number 1 is on page 239. So 1 through, yes, definitely. Let's do 1. Let's do 1 through 41. And if you want to do odd, that's fine, but you might want to look at doing the evens just so you don't miss something. But 1 through 41 odd would be solid. Okay. Good. Okay. So now we're going to go into chapter 6. And today I'll probably just get through 6.1. I don't see us getting past that. 6.1 is kind of a thick section. The first thing your book talks about, really chapter 6, is titled, I believe, discrete probability. Make sure I'm on the page. Yeah, discrete probability distribution. So we're going to get into actual distributions in chapter 6. So we're not really going to be talking about samples anymore. It's more about distributions and kind of how things are distributed across, certain experiments and things like that. So the first thing your book has to go over is the random variable. Your book defines it as the random variable is a numerical outcome of a probability experiment. Notation: random variables are usually denoted by uppercase letters, okay? So you've got the random variable, which is just what happens when you run an experiment, okay? It's the numerical outcome when you run the experiment. It's not a big deal. But from this random variable, there's 2 different kinds of random variables. There's just discrete, which we're going to talk about in chapter 6. And we've talked about this already on the last test. Discrete and continuous, right? Remember, a discrete random variable or a discrete variable is one whose is very defined outcomes. So your book says a random variable whose possible values can be listed. The list may be infinite, for example, the list of all whole numbers. But things like, the outcome on a die is very discrete, right? The number of siblings. That's a discrete variable. Like number of students in a class. These would be all discrete variables, okay? All discrete variables. Continuous though are a little different because they can take on any value in an interval. So like height would be continuous, right? Weight. Something else your book kind of goes over. Yeah, like amount of electricity used. I'm just stealing it from the book. Amount of electricity used, something like that. Those are all continuous variables, right? They're all continuous variables. So discrete, very like whole number-esque, where number of siblings, number of students in a class, the outcome from flipping a coin is discrete, right? Heads or tails, very discrete, okay? And now we've got to define probability distribution. So probability distribution for a discrete random variable specifies the probability for each possible outcome. So specifies the probability for each outcome. Okay, for each outcome. So if we looked at something kind of basic, let's do like a very, very basic one, like flipping a coin. If I wanted the probability distribution of flipping a coin, it's written a very particular way. Okay. If I was going to flip a coin, this first line, which is X, it's the type of outcome. We've got either heads or we have tails, right? Those are the two outcomes. This is going to be the probability of those outcomes, which we know is just 0.50 for both, right? That is a very, very basic example of a probability distribution, okay? Very, very basic example of a probability distribution, excuse me. Okay, your book does one, and if you want to look at it, it's on page 255. It's a little more in depth about like a fair coin is tossed twice. Let X be the number of heads that come up. So the number of heads that come up, find the probability distribution. Well, let's just do that. So we flip two coins. Let's think. So if we flip two coins, we can get heads, heads. We get heads, tails, tails, heads. We get tails, tails, right? And that's the four outcomes. So now we flip two coins. These are the four different outcomes. So then they want to know what's the probability number of heads, probability distribution for number of heads. So again, if we make this one's a little different. Like if you look at our four different things that can happen, and if we're looking at number of heads, so X is, so again, this line's what can happen, this row. We could have no heads, right? No heads, we get two tails, right? No heads. That happens 1 out of 4 times. So 0.25, right? We could have one head. That happens twice here. 2 out of 4. So that's 0.50. Or we could have both heads. So 2 heads, right? And that's going to happen 0.25 of the time. Okay. So the probability distribution for number of heads would look just like this. These are the outcomes. You could have, you can have no heads, 1 head, or 2 head. And then because we only flip 2 coins, then the probability of no heads would be 0.25. That happens here, right? Probability of 1 head, that happens twice. So 2 out of 4. And the probability of 2 heads, that happens 1 out of 4 times. Okay? 1 out of 4 times. Okay, so your book then says, remember the probabilities all are between 0 and 1. This is stuff we already know. And the sum of the probabilities has to add up to 1. Okay? And now I'm going to kind of just run through a few examples in the book just so we kind of have an understanding of what's going on. So this is example 6.4, page 256. And it says, 4 patients have been appointed to have their blood pressure checked at a clinic. Let X be the number of them who have high blood pressure. So high blood pressure. Based on data from the National Health and Examination Survey, the probability distribution of X is given. Okay, so hold on. Have made appointments to have their blood pressure checked at a clinic. Let X be the number of them. Oh, okay, so what they found is if there's 4 random people that come into this clinic, the probability that only one of them will have high blood pressure. Actually, I'm sorry, we got to start with 0, right? The probability that none have high blood pressure is 0.23, okay? The probability that none have high blood pressure is 0.23. The probability that one and only one has high blood pressure is 0.41. The probability that 2 have high blood pressure is 0.27. 3 is 0.08. Now, the probability that all 4 is 0.01. And now look, these have to add up to 1 because this is all the options that we have, right? If 4 people come into our clinic and we want to know what's the probability of none, 1, 2, 3, 4 having high blood pressure, this is it, right? 5 can't have high blood pressure because there's only 4 people, right? So if we add those together, I'm going to do that real fast just to check it. So 0.23 plus 0.41 plus 0.27 plus 0.08 plus 0.01. Boom, 1, right? 1.0. It's everything that could happen. So this is a probability distribution for 4 patients coming into the hospital or coming into that clinic. So now let's answer what they're asking. So they want to know what's the probability of 1. So what the question is stating is what's the probability that we only have 1 patient with high blood pressure? Well, that one's kind of easy. It's 0.41. Okay, it's right there. So B says, what's the probability of 2 or 3? Now look, 2 and 3 are mutually exclusive, so we can just add them together, okay? Because they're mutually exclusive, remember the Venn diagram stuff, there's no overlap here, right? We can't have the probability of 1 happening and the probability of 2. That doesn't really make sense. So because of that, you just add these together. So we get 0.27 plus 0.08. So you wind up with 0.35, right? 0.35. Then part C says, what's the probability more than 1? More than 1. So, I mean, I assume what that means is 2, 3, 4, right? So more than 1, the probability of more than 1, so that would be the probability of 2 plus the probability of 3 plus the probability of 4, right? So I'm going to use my calculator here and I'm going to add up 0.27 plus 0.08 plus 0.01, and you wind up with 0.36. Okay. And then the last one is the probability of at least 1. At least 1. Now look, we can add up 1, 2, 3, 4, right? 1, 2, 3, 4. You're more than welcome to do that. And you know, honestly, we have calculators, it's not gonna take that much more time. But I want you to get in this habit where if it's at least 1, that's the same as saying 1 minus the probability of 0, right? We know all of these add up to 1, right? So if I wanted all of these probabilities, I could just say 1 minus the 0.23. So 0.77. Okay, 0.77. That's a good example. Okay. Questions? Lori, make sense? It's not that bad. It really isn't that bad. This is what's kind of neat is we can do some really neat real world stuff in this section. Okay.
Yeah, so far this looks pretty easy.
It really isn't that bad. It'll be, we're building, this is the foundation that we're going to build on. Okay. So not that it gets harder per se, it's just that it's a foundational thing. Okay. So let's look at the next example, because now we're going to connect between probability distributions and populations. And I'm going to just read from the book. It says statisticians are interested in studying samples drawn from populations. Random variables are important because when an item is drawn from a population, the value observed is the value of a random variable. The probability distribution of the random variable tells how frequently we can expect each of the possible outcomes or possible values of the random variable to turn up in the sample. So, and then we're going to go over 6.5 for a minute. So an airport, this is example 6.5. An airport parking facility contains 1,000 spots. Okay, I'm going to write that down. We're at the airport, we got 1,000 spots. Of these, 142 are covered long-term. And that covered long-term, and they're $2 per hour. Okay, 378 are covered short-term, so covered short-term. And they are $4.50 an hour. Okay, 423 are uncovered long-term, so uncovered long-term. And uncovered long-term is $1.50 an hour. And 57 are uncovered short-term. So only 57. Uncovered, but then short-term. And they are $4 an hour. Okay. And look, this is all that can happen. If we add these up, I'm going to do it real fast just to make sure our math's right. 57 plus 423 plus 378 plus 142. Yep, adds up to 1,000. Okay, so here's all the different spots broken down, right? Now it says a parking space is selected at random. Let X represent the hourly parking fee for the randomly sampled space. Find the probability distribution. So now our X value is the cost of the space. Okay, so the X value is the cost of the space. We know we got 4 different costs, right? We got $1.50. We got $2. We've got $4, and then we got $4.50, right? So if we just randomly walked out there and chose a spot, they want to know what's the probability you choose a spot that's $1.50. Okay. Well, $1.50, look, there's 423 spots that are $1.50, right? 423 out of 1,000. Now what's nice is, yeah, it's good. We're about 1,000. It's just 0.423, right? So the probability we randomly choose a spot that's $2. I know this isn't random. You go, oh, hey, it's covered or it's uncovered. But let's just imagine that we, threw a, we're flying in a helicopter above it and we throw something and it lands on the spot. Okay. What's the probability you hit a $2 spot? Well, there's 142 out of 1,000 that are $2, right? $4. There's 57, so that's only 0.057, right? And then 450 is the, wait, 450 is 375. So, oh, no, that's 378.
378.
Yeah, 378. Now notice if you add these up, and I'm going to do that real fast, they should equal 1. So 0.423 plus 0.4142 plus 0.057 plus 0.378, 1.00. Okay, all of these add up to 1, and these are the only 4 options we have when it comes to pricing of the airport. Yeah. Okay.
Okay.
Not a big deal, right?
Mm-mm.
No, it's not. And then your book gets into probability histograms, and it just makes a histogram out of the different options. Now, look, it does a totally new example. I'm going to do one just based on our parking lot example. Because it's discrete, your bottom, if you made this histogram, which, I mean, we're not going to have to worry about this on a test. We might have to get information from it, though. Look, if we're going to make a histogram out of this, we've got 4 different groups here. So we've got the $1.50 group. We've got the $2 group, the $4 group, and the $4.50. And I know what you're thinking. You're thinking, hey, wait a minute, that's not the correct number of units. But remember, this unit doesn't matter. It's just that's just the describing the type of spot, right? So our highest probability was 0.42. So I'm going to go up by 0.10. So 0.10, 0.20, 0.30, 0.40, and 0.50. Okay. So this is our probability of occurring. This is the actual X value, right? Now histogram, remember, we're going to put the bars together. So 1.5 was 0.423. So about right there. 2.0 is 0.142 is about right here. Now, no, this isn't the best example because like that bar's way wider. That's just because I'm human, okay? 4 was real thin, so 0.05 about right there. And then 0.4 or 4.50 is about like that. So this would be our probability histogram. Notice that the Y values are the probabilities, okay? The Y values are the probabilities in this example. Ooh. Okay, yeah, 15 more minutes, right? Ooh.
Yeah.
You know what? Let's stop there, and I'll finish 6.1 tomorrow because the next thing we're about to get into is going to take longer than 15 minutes. And it actually comes with some really cool examples. So I'm not going to give homework on 6.1 yet. I'll do that tomorrow. So just get the 5.4 homework done, and then we'll do 6.